Good morning, sir. So today I'm going to discuss a research entitled Design of Adaptive Active Noise Control using LMS and FIR filter for vehicles. Abstract. The active noise control system for vehicle is proposed in this paper. Noise from sources such as engines can cause a person a physical and psychological stress, reduce productivity, disrupt communication and concentration, and contribute to workplace accidents and injuries by making warning signals difficult to hear. To cancel this unwanted sound, the researcher proposed a system that uses microphones and loudspeakers to generate an acoustic wave that can potentially reduce the sounds. The focus will be on using adapted digital signal processing to solve the problem. A one-of-a-kind solution to problems caused by the application's acoustical nature will be presented. This includes a discussion of the LMS algorithm and the use of FIR adaptive filter. Statement of the problem. The purpose of this study is to develop a design of a system for controlling the noise caused by vehicles using LMS algorithm and FIR filter. Specifically, this study aimed to determine the following. What methods will be used to develop the proposed system? How effective is the proposed system in reducing the noise from vehicles? Is there a significant difference between the original sound and the controlled one? Solution. Active noise control tries to reduce the level of unwanted noise propagating through the air by using an electroacoustic system comprising measuring sensors such as microphones and output actuators such as loudspeakers. The active noise control system provides a anti-noise that attenuates undesirable noise in a desired quiet region using an adaptive FIR filter. In developing the system, the researcher used the method of integrating the least mean square algorithm and FIR filter to produce an active noise control system. Reduction or elimination of noise is one of the most important applications of an FIR filters. These filters generate an equal but opposite phase signal which acts on the noise signal to reduce or cancel it. Least mean squares algorithms are used to simulate a desired filter by determining the filter coefficient that produces the least mean square of the error signal, or the difference between the desired and the actual signal. This technique can be adapted to dynamic noise environments.
This is the figure for the LMS-based FIR filter. First, there is the input, which is the sound that will be transformed or reduced. Next is the filter, where the whole process of transforming the sound happens. Lastly is the output. In addition, you can use the formula to find estimation error.
This is the formula for finding the error of a signal. The error signal is calculated by comparing the actual output to the desired output. The output can be calculated using y is equals to b is equals to summation of w sub I times x sub I is equals to w times x, where x is the input vector and the w is the coefficient vector. The impulse response of the second direct propagation path is calculated by the system. Within the quiet zone, the anti-noise takes the secondary propagation path from the output loudspeaker to the error microphone. This phase is commonly performed prior to noise control using a synthetic random signal played through the output speakers while the unwanted noise is not present.
This the output signal after it undergone the estimation of the secondary propagation path. It is very important task to know if there is a connection between the output loudspeaker and error microphone.
The next step is to design the secondary propagation path estimate. For effective control, the length of the secondary route filter estimate does not need to be as long as the actual secondary path in most cases. The normalized LMS algorithm is used to make it simple and reliable.
This the result after using the FIR filter to the inputted signal. As you can see, we can almost identify the output, the desired, and the error signal.
The accuracy of the path estimation is the next step. The true and estimated path coefficient is shown in the diagram. The only part of the true impulse response that is not accurately approximated is the tail. During operation in the designated task, the residual error has no significant impact on performance of the active noise control system.
This is to test if the secondary path impulse response estimate is accurate.
Finally, the noise propagation path to be cancelled. A linear filter can be used to characterize this noise, since linear filters generate output signals from time-varying input signals.
This is the path where the noise to be cancelled will take place.
Results and discussion. An adaptive active noise control for reducing the sound coming from the vehicle was suggested. The system has undergone several steps in order to meet the goal of the study. The system is experimented and simulated using MATLAB software. Based on the result, the proposed system is effective in reducing the noise from signal as shown in Figure 6. The benefits of the system includes the use of few resources and requires few calculations. When the location of sensors or the propagation path are changed, the adaptive structure is capable of estimating and converging to a new acoustic path characteristics in a short period of time.